Okay, so what we're doing here is we are looking at more complicated functions than we've dealt with so far in this section, but trying to apply the rules that we've developed to finding the derivatives. So notice here I have a fourth degree polynomial. And again, if you tried to evaluate the derivative of this function using the limit definition, that would be horrible. This is very, very large type, as a very complicated polynomial for doing that kind of a thing. But fortunately for us, we don't need to go through all of that work. Y prime is by definition the derivative of this. I'm actually going to be writing more work in this example than I would normally do when differentiating a polynomial, and this is only to show you where the rules that we just talked about come into play. So because this polynomial is a combination of differences and sums of these different terms, my sum and difference rules that we proved at the end of the last video allow me to take the derivative of each one of these independently. So this is equal to d dx of x to the fourth minus d dx of 2x cubed plus d dx of 5x to the 5x squared plus d dx of 7x plus d dx of let's call it minus d dx of 1. Okay, and again, normally you're not going to have to write all of this stuff out. You'll be able to do all of the work in essentially one step. This is just to illustrate how we're using our rules. All right. Now, I'm going to keep this first term the same. All I've done from this step to this step is applied my sum and difference rules. I brought this d dx into each term individually. Now I can use my constant multiple rule. Some of these expressions have coefficients in them. So the 2 here, for example, by my constant multiple rule can be brought outside of the derivative. So this becomes minus 2 d dx of x cubed plus 5 d dx of x squared plus 7 d dx of x minus d dx of 1. I technically don't need all the parentheses here, but I'm putting them there for consistency. Now I can evaluate each of these derivatives simply by using my power rule. D dx of x to the fourth would be 4x cubed minus 2 times the derivative of x cubed, which would be 3x squared using my power rule, plus 5. My derivative of x squared would be 2x to the first power, which I just write as 2 to the x, plus 7. We had a rule all the way back, or a while back, that we've discovered that d dx of x is simply equal to 1. Using the power rule, I could show that by writing an exponent of 1 up here. The power rule would then have me bring the 1 out front, so it becomes 1 times x to the 0 power, but x to the power of 0 is simply 1 anyway, so this derivative is going to just equal 1. And then finally, the derivative of any constant function is 0. I'm not going to bother writing minus 0 here, I just know it's going to go away. Finally, simplify things. 4x cubed minus 2 times 3 would be 6x squared, plus 5 times 2 is 10x, 7 times 1 is just 7, okay? Now, even though that's substantially faster than using the limit definition, like I said before, in the typical example, you're going to be jumping straight from this step all the way to this step, because look at what we would be doing. I'm just going to think of using the power rule on each term independently. That's basically what we did. 4x cubed, that would be my power rule here. If I use the power rule here, the 3 that comes down is just going to get multiplied to that 2, giving me minus 6x squared, And then I do something similar for each term. You don't need to write all of this in a typical example. Let's do part B using that faster approach. So f of x is given to us up here, but I'm going to rewrite all of my terms in as power functions. So x times the cube root of x, that's x to the first power times x to the 1/3 power, which is the same thing as x to the 4/3 power, okay? Minus, this is 4 over x squared, which is the same thing as 4x to the negative 2nd power. And now I'm just going to differentiate this, and I'm not even going to bother writing all of those ddx's like I did in the previous example. I'm just going to apply the power rule. So the 4/3 comes down here, multiplies with the 5, giving me 20/3. Then I subtract 1 from my exponent, x to the 1/3 power. The negative 2 comes down here and multiplies with this negative 4, giving me positive 8, x to the negative 3rd power. And you see that was way faster, and that's typically what it's going to look like when you do these derivatives. Okay, so no problem there, easy stuff. Okay, here's another example. We want to find the equation of motion of a moving particle given by, we have the equation of motion of a moving particle given by s of t equals this cubic polynomial here, and we want to find the acceleration of this particle as a function of time, and then determine the acceleration of the particle after 3 seconds. So the equation of motion, even though I don't think I used that term before, I was calling this a position function when we did these moving particle on a number line examples before. It's the same thing. Equation of motion just tells me the position of a moving particle at some given time t. The question only asks for the acceleration of this particle. And we talked about this in a previous section in chapter 2. The acceleration is the derivative of your velocity function, which is the derivative of your position function. So that makes the acceleration function that we're looking for the second derivative of s of t. So first, that means we're taking two derivatives here. S prime of t, which is the same thing as v of t, is equal to the derivative of this, which I can use my power rule on to find very quickly. Power rule here, bring the 3 down, multiply that to the 4, I get 12t squared. Bring the 2 down, I get minus 2t to the 1st power. It just looks like minus 2. Minus 5t is going to have a derivative of simply minus 5. Look at how quick we did that. Acceleration is equal to the derivative of my velocity function, or the second derivative of this. So I'm just taking another derivative here. Bring the 2 down, I get 24t minus 2 times, just minus 2 actually, so this would be minus 2. And there is my acceleration function as a function of t. It also asks us to find the acceleration of the particle after 3 seconds. A of 3 would be equal to 24 times 3 minus 2. That's equal to 70. And we know that we're measuring time in seconds. It doesn't indicate what the units of distance are, or displacement, but typically they're going to be meters, so I'm going to just say meters per second in this case. Meters per second squared, because that's the units that we would use for acceleration. Okay? Pretty straightforward. So now we're going to move away from the power rule and move into the exponential function. Now, in order for this section to really make sense, you do need to understand something about the exponential, or the number e. Okay, so you would have talked about the number e in intermediate algebra, pre-calculus, college algebra, any of those courses. You should absolutely be familiar with that function, or that number. It arises, I think the first time you talk about it, it'll arise in the topic of continuously compounded interest. But the number e, by definition, is this: the limit as n goes to infinity of 1 plus 1 over n to the power of n. Now, when you talk about the number e in an algebra class, you probably wouldn't have used the limit notation. You probably would have given this expression, 1 plus 1 over n to the power of n, and this would have come out of your concept of compound interest. And then you would have said, as n gets bigger and bigger, this expression seems to be approaching some number around 2.7 something. And then we just say, whatever that number is approaching as n gets bigger and bigger, that's what we define e to be. But that idea of approaching, we now know can be reframed in terms of limit. So as n gets arbitrarily large, another way of saying that is we want the limit as n approaches infinity, okay? So for us, this is what we define the number e to be. And there are other definitions for the number e that are equivalent to this one. Your book in this section will give a different definition for the number e, and we're going to try and connect those two here. So I'm just putting that there because we're going to refer back to it in a moment. Let's suppose that we wanted to find the derivative of just a general exponential function. F of x equals b to the x, where b is greater than 0 and b is not equal to 1. These conditions will show up in any definition of an exponential function, okay? So if that's our definition, then f prime of x by definition would be this. The limit as h approaches 0 of our difference quotient. And given the way that we defined f of x here, f of x plus h is the same thing as b to the power of x plus h minus b to the x. That's my f of x. Using my exponent rules, b to the x plus h is the same thing as b to the x times b to the h. You know that from elementary algebra. But now I see that I have a factor of b to the x showing up in each of these terms, so I could factor that out. B to the x comes out here. Okay? Now, the limit is concerning itself with the variable h, which shows up in a couple of places, but there is no h in this term here, in this factor, b to the x. So that means the limit will not have any impact on that b to the x, and for that reason, we get to treat it like a constant. It can be brought out of the limit using the limit law that allows you to do that, okay? And then if you look at what's left in here, the limit as h approaches 0 of b to the h minus 1 over h. This is the same thing as f prime of 0, and the reason I know that is because this numerator right here can be rewritten this way. B to the power of 0 plus h minus b to the power of 0. 1 is the same thing as b to the power of 0. This is the numerator we would expect to be seeing here if we were evaluating our derivative at this specific number 0. Okay? The b to the x just got to escape that limit. So what this means for us, remember, our original function, f of x, was defined to be b to the x. And the derivative of that was ended up being equal to a constant times that original function that we started with. Because I'm plugging a number in here, f prime of 0, that's a constant. Another way of saying the same thing is that for any exponential function, its derivative is a function that's directly proportional to the original function. That's not something that happens with other functions. That's a unique property of exponential functions. Now, f prime of 0, which would be what we call the constant of proportionality in that previous description I just gave, will equal different numbers depending on what b is, depending on what the base of your exponential function is. And a really interesting case is when f prime of 0 is equal to 1. Because if f prime of 0 is equal to 1, then we get f prime of x is just equal to b of x. But b of x, or b to the x, was the original function. So if f prime of 0 is equal to 1, then f of x is its own derivative, which is a really interesting property for a function to have, to be its own derivative. So the question arises, what value of b will allow f prime of 0 to equal 1? And it turns out that occurs when b is equal to e, the number that we gave a definition for up here. Okay. Now I think I have a handout that walks through the proof of this much more carefully. And I'm going to see if I have it. If I do, I'm going to post it to our Canvas site. But what I'm going to do here is walk through an informal argument for why e is the number that does this. So notice what we're looking for. F prime of 0, which was given by this limit right here, the limit as h approaches 0 of b to the h minus 1 over h. We want to show that this limit comes out to 1 if this number b is equal to e. And in fact, your book simply defines the number e using this limit. But because you would have seen a different definition for e in algebra, I want to connect these two things. So let's suppose that we have some value of b such that the limit as h approaches 0 of b to the h minus 1 over h is equal to 1. We want to figure out what b would have to be for this to be true. So what I'm going to do is do sort of an informal thing with limits. This means that if h is sufficiently close to 0, then this expression is very, very close to 1. Or in other words, b to the h minus 1 over h is approximately 1. Okay? So I'm going to work with this, and I'm going to treat that approximately symbol as if it were an equals sign and do some algebraic stuff with this equation. It's not an equation, it's got an approximately sign. But if I multiplied both sides by h, I would get this. Add the 1 over, I would get this. Take the 1 over h power of both sides to cancel that h out, and I would get this. Okay? Now, this expression is sort of similar to what we're seeing in our definition of the number e, but we need to make a variable substitution. And before I do that, I want to point out that, again, this approximation gets better and better as h gets closer and closer to 0. So if we were to take the limit as h approaches 0 of this expression, we are expecting b to be exactly equal to that limit. But we're also assuming that that limit exists in the first place. And if that limit exists in the first place, then both the right and left-hand limits as h approaches 0 would also have to exist and equal the same number. So I want to focus on just the right-hand limit. H approaches 0 from the positive side or from the right would give me the same limit if applied here. Now, I'm going to define a new variable n as the reciprocal of h, which means h is also the reciprocal of n. And from that definition, using this guy right here, if h is approaching 0 from the positive side, which means I have a positive over a positive, this rational expression here will be approaching infinity, positive infinity. Okay, so if we take the limit as h approaches 0 from the right, then n is approaching infinity. That means if I want to deal with that limit, I can make a substitution. The limit as h approaches 0 of 1 plus h to the 1 over h power, put in terms of n, is equal to the limit as n approaches infinity of 1 plus, now remember, h is the same thing as 1 over n, and 1 over h is the same thing as n. So there's where the substitutions come into play. But this is exactly how we define e. Okay? So that gives us some justification for this. Putting all of that discussion together, what this means is that the derivative of the exponential function, or sometimes it's called the natural exponential function, e to the x, is itself. It's its own derivative. Okay? So now we're going to do a couple of examples before we wrap things up. We have this function y equals e to the x minus x squared plus 4x. We want to find y prime and y double prime. Y prime, my derivative, I can do term by my sum and difference rules. The derivative of e to the x is itself, e to the x. Minus x squared using the power rule, the derivative would be 2x, plus 4x, again for my power rule, derivative would be 4. Done. Y double prime, want the derivative of this guy. The derivative of e to the x is itself. Derivative of minus 2x is minus 2, and constants have a derivative of 0, so we're not going to write that. Look at how quickly we were able to do that. Okay? Easy stuff once you know these rules. Last example. I'd like to find a point on the curve y equals 2e to the x at which the tangent line is parallel to the line y equals 4x minus 1. Don't get too caught up in this. This problem is not as hard as it might initially look. Remember that two lines are parallel if they have the same slope. So the only reason we need this is to get the slope. M equals 4, okay? I'm just looking at the slope of the tangent line right there. So how do we find the slope of a tangent line to some arbitrary point on this curve? We would need its derivative. What is y prime? Well, the derivative of 2e to the x, remember, is I use the derivative of e to the x is itself, and the constants by my constant multiple rule just kind of stay there. So this is also its own derivative, okay? But I'm looking for a specific value of x that would give me a slope of 4. And because this represents the slope, I set this equal to 4, okay? 2e to the x equals 4. Dividing both sides by 2 gives me e to the x equals 2. And to solve for x, you need a natural log. So x is equal to the natural log of 2. I don't need to put that into a calculator. Just like with radicals, we consider it to be in simplest form if we leave that natural logarithm alone and just say that this is our answer. Now, I boxed that off, but I should actually be finding the y-coordinate, because it says find the point on that curve. This is just the x-coordinate of that point. So to find y, I would be plugging this in to my original function, y equals 2e to the natural log of 2. In a natural logarithm, the natural logarithm and the exponential function are inverses of each other. Those cancel each other out, giving me 2 times 2, which is 4. So actually my answer is, not that, natural log of 2, 4. That would be the answer. Okay, that's going to wrap up section 3.1.